Now, if we think of the number line, and we have some numbers here. It doesn't really matter where we are on the number line. If you say, let's suppose this is a 5, 6, 7, 8, 9. We can be wherever we want. 2. If we have a calculation like 5 plus 2, then our number line model said, stand over there, because you're adding, you're looking, you just snowed, you played in the snow, you're happy. You're looking to the right because you're looking in the positive adding direction under normal circumstances. And you're taking a positive 2 steps forward. So you'll be over there, obviously. If I now compare that to 5 minus negative 2, I'll do it up above the number line. What does that mean in terms of my number line model? I'm standing at the first number. I'm looking left because I'm subtracting, so I'm looking into the negative side, the lower side. But then I'm walking backwards 2 steps. So either way, I'm going to be at 7. Now intuitively that makes sense. If you think about yourself, looking that way and walking forward as you're facing, and turning around and walking backwards should have the same effect. So on the intuitive side, we can understand how these two are the same. That adding, feel free to close that door at the back. People are noisy. Outside people, not us. So with this sort of physical, visual understanding of how to perform the arithmetic, we can easily verify and be confident that these two are the same. So adding a positive integer is the same as subtracting a negative integer. And then that sort of leads to the shortcut of 2 negatives make a positive. And there's not much thought going into that. We can certainly stay on the intuitive side with that. But there's a little more going on that I just want to be aware of. And this, just note, this still applies on my circle. If I now have a 0 there and a 1, 2, 3, and whatever, I'm still walking around with addition and subtraction. I'm still walking around the line in the same way. Sorry, that 2 is not positioned very well. Let's do the whole circle. I have my 6 there, 9, 10, 11, 4, 5, 8, and 7. Wherever I am, this would be exactly the same, except there is no negative 2. So let's talk a little bit about the circle, since my numbers are more limited, and it forces me to really look at these two things and why they're the same. So let's have an observation. Let's note, which is the one I have in the book, just to be consistent. 8 minus 5. 8 minus 5, and I'm working mod 12, just to have a familiar circle. Now 8 minus 5, I can do it by walking around. I have an 8 here. 1, 2, 3, 4, 5. So it is 3 mod 12. But if I'm at if I'm trying to get to 3 as my answer, and I'm starting here at 8, because of the circular setup, I can get to 3 in 2 different ways. I can get to it this way, which is what this did, or I can get to 3 the other way. So we also have that 8 plus 1, 2, 3, 4, 5, 6, 7 will give me the same answer. So I prefer to look at this discussion with the modulo whatever circle, 12 for convenience, because the number lines naming system of my numbers are almost so convenient I can't look past them. Here all the numbers are different, and they don't. This one doesn't look like this one. None of them look the same in any way. And my addition and subtraction walking method, if you want to think of that model, is exactly the same. So I have these 2 ways, starting at 8 in both, and ending up in the same way, one with addition and one with subtraction. There is a special relationship between 5 and 7 mod 12. What could be the relationship between them? That if I change these numbers, the relationship between these 2 numbers that feature here will still be the same. Well, maybe we don't know. So let's have another example. Let's try, I don't know, 6 and 2. So let's suppose we start at 6. And we want to add something to get to 2. Actually, we did subtraction first, so I guess let's do subtraction first. Clearly, minus 4 to get to 2. But I can also go the other way by adding, and eventually I'll come around to 2. What would I have to add to 6 to get to 2?
9.
Start here. 1, 2, 3, 4, 5, 6, 7, 8. What is the relationship between 4 and 8, just like 5 and 7? Not clear yet? Let's do another one. Random number?
4.
4. And random answer?
6.
6 got you. So it doesn't matter, right? We don't have to be bigger to smaller or anything like that. Though it would be better, so I'm going to just pick an 8 here just for keeping it as simple as possible, but it doesn't really matter. So clearly I have to subtract 2 to get to 6, but I can also go the other way by adding something until I get to 6, taking forward steps. Where am I? 8. All the way to 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the relationship between 2 and 10? So now I'm gathering evidence here. Those aren't random pairs of numbers. What do I see? They add up to 12. They add up to 12. And if I keep doing that, they're always going to add up to 12. So let's give a name to these numbers. Given 1, let's suppose I've done the 5. What is the other one that would give me the same result if I added instead of subtracted? I should not have done that. Pretend everything was still here. Let's say like this. We call 5 and 7. I have to specify additive because I'm doing plus and minus, inverses, and of course I'm working mod 12. It depends what I'm working with, because when, or let's say because, what was the link? 5 plus 7 I'm not going to say 12 because there is no 12. I'm going to say 0 instead. But 12 and 0 sit at the same place. So we call them inverses in the additive sense because there are other things, multiplication, other things happening. We're just working with plus and minus. So if the context is clear, you don't have to say additive and inverses. You can just say inverses if nothing else is happening. When I add two numbers together and I get a 0, which I do. 4 plus 8 is 12, which is 0 mod on this circle. 2 plus 10 is also 0. So I get these special pairs of numbers. Special pairs of numbers. Given 1, I can very easily find the additive inverse of that number. Whatever number will get me to 0. And 0 can be different things depending on the arithmetic system that I'm working in, whether it's a number line or a circle. So before I do a definition, let's do 13.3, and I'll update that in a second. And 4 examples. 4 examples. What is the additive inverse of 6 mod 13? Now I can't look at this circle anymore, right? Because if it's a different modulus, the circle is different, just bigger or smaller. So let's write it like this. Additive inverse of 6 mod 13 is 1. So I'm looking for the number that when I add it to 6, I get a 0. 7. 0 and 13 are the same, right? So I'm just going to say here, additive inverse, just a little shorter, of, the next one is 8. Mod 24 is, well, the 24 circle is big. It goes from 0 to 23, so I have a lot of options. 16 is what I'll have to add to 8 to get to 24, or 0. And the additive inverse of 4 mod 9 is 5. Additive inverse of 5 mod 8. 3. So it's not a hard number to find. Depends on the size of my circle. Whichever number gets me back to 0. Now we'll see why and what to do with these. We're just observing that there are special pairs of numbers. Among other special pairs, this is the special pair that I want to focus on, and we give them names, additive inverse. Now, in general, I don't want to write this many words, right? There's nothing wrong with writing words. But given a number, I want to name its additive inverse with a name that relates to the given number. So instead of saying the additive inverse of 6 mod 13 is 7, I know it is 7, I just want to give it a name. My naming is going to be 6 with a little negative in front of it. That has been the way that someone proposed it one day, and people said, yeah, that sounds pretty simple, let's go with that. And then we can say that is 7 mod 13. So we're not saying anything new or different, we're just writing it in a more compact, efficient way, which is really what math is all about, to some degree. So I'm just updating these. The additive inverse, what were we working in? 24, we said was 16. This one was the additive inverse of 4. Mod 9 was 5. It's saying the same thing, just translating it from an English sentence to a mathematical sentence. Now I cannot remember what we were doing last. On 8. So the additive inverse of 5 mod 8 was 3. So the sentences are the same, just a translation, just for efficiency or laziness, whichever one you want to look at. So in general, I can give you any number. Let's actually leave this 8, 7, and 5, and 3 a little bit longer. In general, the additive inverse of a number, let's call the number A, to be consistent with the book, always exists. It depends on the number line in question and has general name a negative in front of the given number. Now on my circle, I don't have these -6, -8. That's how we call it a -6. That number is not on my circle. The 7 is on my circle. So it's just a temporary name, this negative in front of the number, sort of a temporary name. Before I figured out what number it actually is, I can just give it a name so I can talk about it. That is not necessarily something that is on my circle. I have to figure out, well, what is its other name that does appear on my circle. Now, the thing is, when we look back at this, what does my initial observation tell me? Here, so these are additive inverses of each other. So if I start with an 8 and I subtract the number, it is the same as if I started with my 8 and added its additive inverse. So this 7 is, no, I write it like this or the other way around. Doesn't matter. This 7 is the additive inverse of 5. This 5 is the additive inverse of 7. So let's just get used to that and then I'll come back to this again. So what that means is something profound that no one really thinks about anymore. This technically means that there is no subtraction. Subtraction is simply, can be rewritten, any subtraction, like 8 minus 5, can be rewritten as an addition. These two are the same. I can get to 3 by adding the appropriate number, the additive inverse. So in that sense, subtraction isn't something that I have to ever do. It's not anything new, because any subtraction sentence like this can be rewritten as an addition sentence. So subtraction is not really giving me anything new. The only reason it was introduced and sort of developed as if it's a separate type of arithmetic, or a separate arithmetic operation, is because of its intuitive help, where I'm taking away something. That concept is easy to understand. Where I'm adding something to my object, subtraction can be intuitively viewed as taking away. So on the intuitive side, it has a lot of benefits to see them as separate, but mathematically they're not separate at all. There is only addition. Subtraction is a lie. There is no subtraction. Now let's practice 13.4 just to let that sink in a little bit. That doesn't mean never do subtraction. It just means it's not actually a brand new operation. Doing something to two numbers and getting a new number. It's just addition in disguise. 13.4 says Write the following subtraction problems as addition of the appropriate additive inverse. So we have a number 1, 9 minus 6. How do I write that as the appropriate, as an equivalent addition sentence? And of course I'm working mod 13, that's important to know. Now if we look at this, how do we figure that out? You can figure that out in two ways. One is find the answer and then see what you have to add to find the same answer. But if we do this enough times, we'll notice that these two numbers, one subtracted and one added, are additive inverses of each other. So you don't actually have to know the answer at all. Not that it's hard to find, you don't need to know the answer. These two are the same. Now it's not a full sentence unless I have the verb, which is equals, or some version of equals. So it's not really a full sentence that I can say is equivalent to another one. But I can always rewrite the subtraction to an addition by just changing from the 6 to its additive inverse. What is the additive inverse of 6 mod 13? Seven. Because 6 and 7 together will give me 0. Now we can test that. We can say, well, 9 minus 6 is 3. So the answer on this side is 3. So the answer on this side better be 3 as well. 9 plus 7 is 16. Mod 13 is 3. You can do it that way, but that's not really the point. The point is that any subtraction can be rewritten as an addition, which means there really is no subtraction. It's just there for convenience. Mathematically speaking, there is no subtraction. 2. 16 minus 8 mod 24. 16 minus 8 mod 24. The reason we're doing the modulo circle arithmetic is just because then I'm really forced to realize that the additive inverse is another number that has its own name. I just have to find it. So that'll be the same as 16 plus 1. 16. Doesn't matter what the answer is. I don't need to know what the answer is. Any subtraction can be rewritten as an addition with the appropriate additive inverse. 3, 8 minus 4, 8 plus something mod 9. Well, that something is the additive inverse of 4 mod 9, which is 5. And you can test them with answers. Do you get 4 in both cases? I'm not changing anything. I'm simply rewriting the subtraction. 7 minus 5. 7 minus 5 is 7 plus something mod 8. Well, the additive inverse of 5 mod 8 is 3. So I can get the answer with a subtraction or an addition. Subtraction doesn't give me anything fundamentally new. It's just a matter of convenience when I'm over on the intuitive side. Now, right now I'm making a big deal of something that you might feel is not a big deal. That could be true, because you can argue the following just by an intuitive number line. But when we get to multiplication and division, especially with fractions, now suddenly my intuition is not so happy anymore. But the underlying structure of how the numbers work is pretty much the same as this. So let's now look at, I'm terrible at moving the camera apparently. Let's look at these, or just one of them at least. Let's say the first one. And say, okay, well, how could I have written this? if I have a 9 plus 7, I can change this 6 and call it the additive inverse of 7. Because those names are this, it's two names for the same thing. 8 and 16 are additive inverses. So this 8 can be substituted by the additive inverse of 16. Because it is the additive inverse of 16. Two names for the same thing. Like you have a first name and a nickname. Still you, just like this would be the additive inverse of 5, just going backwards. And this would be the additive inverse of 3. What does this say? This is in a way saying in general that regardless of the numbers, this would work. If I have a number n, let's say, and I'm adding some other number a, that's equivalent to n minus the additive inverse of a, whatever the modulus, the circle may be. So this means that subtracting a negative number, which is really just the additive inverse in disguise, is the same as adding the, let's just say, positive number, the original. Or, very loosely speaking, two negatives make positive. So now we go to the number line, and their issue was we have the concept of these numbers on the other side of 0. Because they represent owing money and things like that. So it's an intuitive concept. So there's my 0. Now I go to the number line. I have 1, 2, 3, 4, and 5, let's say. I have these numbers over here. How should we name them so that it's super convenient? They didn't have names before they existed. They existed first, and then people decided, well, how should we name these? Well, whatever this guy is the additive inverse of 1. Because when I have 1 chicken and I owe you 1 chicken, I'm at 0 chickens. So they existed before they had names. Maybe not like you. You would have maybe been... No, you existed before you had a name. Like this. This one over here, if I go one step left, is the additive inverse of 2. Because if I had 2 chickens, and I owe you 2 chickens, I really have no chickens. So 2 plus this number is 0. So these numbers are extremely closely related to the existing natural numbers. And therefore, someone said, well, let's just put a negative in front of them. That would make the most sense. So we always visually see they're linked to their positive natural number counterpart. But they could have been named anything. This is a name. It is in no way attached, or it's in no way separate from the 1. That is the name for this number here. But we forget and think these guys can be just moved around and canceled with other things. It's simply because of the convenient naming system that's used. That seemingly I'm canceling these negatives. Only because subtraction by an additive inverse is addition of the number. Then it's named in such a way to easily have those seemingly intuitive shortcuts when we're just really used to them, we still have to understand really what is happening behind here. What is the link between these numbers and the other side of 0? So that's my little blurb to just get you to be a little more aware of these shortcuts aren't actually shortcuts. They're just conveniences of our naming of the numbers. This is the insert for example or exercise 13.5. That's not in the video. Well, it is now. Number 1, we want to use for all these the concept of additive inverses to rewrite these phrases, not equations, not sentences because they don't have an equal sign of some kind, phrases using addition instead of subtraction. So I have 9 minus negative 6. Now negative 6 is the additive inverse of 6. I don't know what its name is, mod 13, and I also really don't care. It's not really what the question is asking. The question is asking to simply rewrite this with addition. So if I subtract an additive inverse of 6, that is equivalent to adding 6. And since I'm working mod 13, I can finish it by saying, well, 9 plus 6 is 15, mod 13 is a 2. But the important part is up here. Number 2, I have 2 minus 8, and I'm eventually working mod 24. So if I subtract, there really, when you break it down mathematically, is no subtraction. Subtraction is the same as addition by the additive inverse of this number. I'm working mod 24, so now I have to find what is the additive inverse of 8. Mod 24, well, 8 plus what is 24? It's going to be 16. And so mod 24, I have 18 as my answer. But the important part is up here when I rewrite it, not finding the answer, but rewriting it to an addition. Let's look at number 3, sorry. In exercise 13.5, number 3 is 8 minus negative 4, and I'm working eventually mod 9. So the additive inverse of 4 is what I subtract. So 8 minus an additive inverse is the same as 8 plus that number. And I'm working mod 9, so 8 plus 4 is 12, 12 mod 9 is 3. Then number 4, I am looking for 3 minus 5. Something's wrong with this pencil. Hold on 1 second, let me fix it. There you go. 3 minus 5, and I'm working mod 8. So if I subtract, that is the same as adding the additive inverse of this number 5. And I'm working mod 8 that I just carry with me until I need to actually find an answer. Well, now I need to know what the additive inverse of 5 is, mod 8. Since 5 plus 3 is 8, the additive inverse of 5 is 3. Now I'm working mod 8, but 3 plus 3 is 6, and I have my answer. So it's about seeing the relationship between subtraction and addition by way of additive inverses. Look at our addition table. Look at our addition table, for example. Like mod, what mod is this? Mod 5. You can pick any one you want. Then we have our addition table, which is a very easy shift of the rows. And you can assign to each number Little graphical, something that's nice graphically. Now there is some structure. If you look at the additive, you pick 0, just empty, just all one color. Then you pick something like this for 1, and something like that for 2, something different. And you can experiment with different things. The additive inverses get the same configuration, but the colors are flipped. So the additive inverse of 1, mod 5, is 4. So you see how they're very similar, but red is black and black is red. Same for these two. They're additive inverses. That would give you a nice diagram in the end. So then wherever you see these numbers, they appear, they get replaced by these 5 bigger squares, and you get what we call mod art. You get that nice pattern coming from the underlying mathematical structure. Now you can of course attach many of these, 3 more of these together to create something that looks pretty nice. Just no, it doesn't. Then you can of course go and say, let's do something similar, but stretch it out a little bit, or compress the bottom right corner a little bit. And if you put those together, you get an even nicer effect. So you can create a lot of different, not illusions, but sort of nice art using this underlying simple arithmetic. This one, I can't quite see where the underlying table, how the underlying table was distorted and what the actual pieces are, but it makes it even more artistic. So, I forgot to hand these out. Probably more than 3, right? Take one hand back. It's done for you in the book, I know, but turn this up and just rotate this back. So an exercise that one can do, oops, now log out, no, subconsciously, is this is one example of something that you could do to create your own mod 4 art in this case. So you take the very simple case. Mod 3 is a little too small, so 4 is a nice starting point, and you fill in the addition table, which we have 9 minutes to do. We can do it. So let's fill in the addition table, and then distort it by sort of squishing the 2 top corners together. So those addition tables should not, especially because it's addition, the table should take you like 5 seconds. Because you're just shifting the rows, there's very little thinking involved. And I think this is discussed in the book as well, but it's sort of done for you. Yeah, towards the end. And I can't afford color printing, so it doesn't necessarily look as good, so I wanted to show it. So you fill that in, and then you copy it over with your distorted table, and you can distort that in many ways, right? This is just one example. Fill in all those numbers. Then now you have to sort of decide on a color combination. One way to make the individual squares more interesting is to split them up into 2 colors, and then we can decide on the colors. The key that makes the mod art visually appealing is that the additive inverses are flipped in color. Additive inverses should have the same basic design, well, they all have the same in this case. But see how 0 and 3, the colors are just flipped. Whatever colors you choose, the additive inverses have to be Just I'll call them the flipped versions, just like 1 and 2 are. Otherwise, your mod art would still be fine, and it just wouldn't have that symmetry and that nice pattern. It's really the additive inverses that give that. So you can pick colors or shadings or do whatever. I'll leave it up to you. You don't have to do it. I'm just running you through it because in the book it's all black and white, so it doesn't show that well. So one thing you could do, I have done it there. Keep going. You can pick some basic colors. Then color the 0, 1, 2, and 3 squares accordingly. So that doesn't necessarily show in the book. A little bit, not really. A and C look pretty similar there, but in fact it's red and blue. Make it even more appealing. Not that the black and white version is bad, still pretty good. And then you put those in place of your distorted table, and you get, where is it? Something like that, which looks nice on its own, but when you make a full circle, it looks even better. And the patterns and the symmetry that you're seeing is because of the additive inverse having the same configuration but the opposite color scheme.